Okay, so I'm going to talk a little bit more about functors, and then we'll talk about the applicative type class. So just remember that. Um, Let me quit out of here and get a fresh interpreter going, and then up here, recall that the functor looks like this. Now, you can have this where what the heck is f here? And it turns out that f is a type valued function that returns a type. So f takes a type, and type value functions, these star is also called a kind. And so, like, what does that mean? Like, if you look at what's the kind of some of the functors that we already know are maybe. Well, maybe is a star arrow star. What's the kind of list? List is a star arrow star. See, maybe is waiting for a type. You got to say, like, maybe int, and what's the kind of maybe int is, oh, that is a type. So what is the kind? Let's say, like, of int. Oh, that's a basic type. But maybe itself is at a higher level. It's expecting a type. You got to give it the type that you're going to inject into it before it becomes the basic type. So maybe is like a function. You give it a type, and it returns a type. The value of it maybe applied to int is an individual type. So functors have to be things. So like we had like instance functor list, where and list down here, you can see the kind of list is the right kind. It's star arrow star. And what do I want to do? I want to define fmap of f on empty is equal to empty, and fmap of f on x const x's is equal to f of x const onto fmap f x's. So that's how lists of fmap is defined for list. And the point is that lists, like if I say, what's the, whoops, let me go down here. What's the kind of list applied to int? Oh, that's list int. Now, that's the same thing as writing what's the kind of list. That these two things are the same thing. One is you're applying this constructor to the type int, and you're getting back that this whole thing is a type. And here you just inject it inside the brackets, and so you get this kind of bracket notation here. Okay, so there were a few. So one way to think about functors is that functors are kind of like containers, because if you can f map both of them, remember, like it's kind of like a container. But what about maybe as a functor? Here we have to say f map, and we got to give it f, and if it's nothing, it's nothing. If it's f map of f over a just x, it's f map of it's just f applied to x. So that's what happens with maybe. Now, functions are also a functor. So you could say instance. Well, so first let me show you the kind. Colon k of arrow is it takes two things. So this poses a kind of a dilemma. Like, it's like, what does it mean then if this is a container? So what you can do is you could say, oh, we've got too many arguments here. Star arrow, star arrow, star. We only want one. So let's plug in something like int. Okay, that is a star arrow star. That's a type that's not completed yet. It's still waiting for some input. So we can make instance functor arrow a, and here I can be abstract. Now this is an interesting case. I say fmap f, and I could give it a name G. And what is that going to be? It's going to be a function that applies f to the result of applying g to x. Now that might look familiar, and so you can actually say, well, wait a minute, copy. I mean, another way to write it, the first way you might think of writing it is like, you might say, okay, x, and here you could say f of g of x. So the result, the elements of this functor type are functions themselves. And so to figure out what the f map of f over g is, well, I got to apply g to x. Okay, but maybe it's more natural to define it this way and say, look, it's going to be a function. It takes an input x, and what does it do? It applies f to the result of applying g to x. But you might recall and go like, oh, wait, that's just the same thing as f composed with g. Oh, but wait, there's an even shorter way of writing this thing down. Once you become, you can say, once you're sold on the functional style, this is one of the reasons why, excuse me, I am suffering from a terrible cold that I'm getting over, but I'm really bad shape. So that's a very simple definition that you could do. Now, if you're in the habit of thinking of functors as containers, then what kind of container are functions from A to B? Well, the function from A to B, the container part, you can think of the range of f. So, in what sense is a function f from A to B a container? How can I think of this as a container? Well, since I had to provide A and it's waiting for a B, the functor is. You can think of this as a container of the range of f. So the things contained in f are the elements of B such that there exists I'll say the elements y in B such that there exists an x in A, x of type A, such that f applied to x is equal to y. Remember, this is called the codomain of the function. This is the domain, and the range is the things that actually get mapped to. So, like, for example, if I had like f of x equals unit equals unit. Well, then what's the type of f? I mean, we could define it down below. F takes any type P and maps it to the type unit. Remember that the type of this thing in the programming language is this thing, the unit type. So this is collapsing everything. So the thing that would be contained in F in this case are, let's say, so we could say, okay, something, more, let's say true. Everything gets mapped to true. Well, then, that maybe is a little bit less confusing. It's a type of F. Oh, it's a P to bool. So bool includes true and false, but the range of F is just true, is the only thing that gets mapped to. Now, it's an interesting thing that, you might think, oh, that's kind of cool. I can think of the function f as, from int to whatever, as containing all the things to the whatever. It's kind of like a set, a way of specifying a thing. The problem is you can't tell if anything's in there. Because if you could solve the halting problem. I might put that in the notes. All right, so that's kind of a review of functors. One thing I guess that's maybe worth pointing out here is that if we look at fmap, type of fmap, we say, okay, that's an A arrow B arrow FA arrow FB. You can think of fmap as taking a function from regular type A to regular type B and returning a lifted function, a function that knows how to work, map from the container type from lists of A to lists of B. So, is that confusing? Let's see. Go down here. I can say like fmap plus 1. What's the type of that? It says, look, as long as f is a functor, this thing here is a function from functors to functors. So how do I apply it? Well, I give it a functor. I could say like it's, just 2. Well, I got to put parens to make it work. That's an instance of the maybe. Okay, or I could put nothing. That returns nothing. I could put, 1 ... 10, and I get 2 through 11. So fmap is applying that function to all of the elements of the list. So if I have like, fmap of plus 1 applied to the function plus 2, let's do it differently. times 2. So this is my, when we were talking about the functor up here, f is plus add 1 and times 2 is the thing that I'm going to do. And so if I say 7, what's the answer here going to be? Well, it's 2 times 7 plus 1. If I swap these around, function that I'm f mapping over is plus 1. And what am I doing? I'm taking the output of whatever that happens when I apply this to something and then applying this function to it. So now here I'm going to have 16 as my answer. So maybe that, I don't know, helps just clear up this function type thing a little bit more. Now, I guess one more thing to say is like, look, what if I say like f map plus 1? What's the type of that? And it tells me, oh, it's got all these types. Whatever functors I have that contain numbers, it will work. You know, anytime I have an instance of a functor that contains a number, this thing will work. So I could say, like, is the type of fmap plus 1 maybe int arrow maybe int? It comes back and it says, yeah, the type of this thing here is this. So it has the correct type. Look, if I put the wrong thing and I say like, oh, that's a function from string to int, it's going to come back and give me an error. So I had to make sure that it was mapping a number type and the same number type. You know, it would be even wrong if error, I think. Maybe not. Let's see. Should be wrong. And yeah, it's wrong if I say integer and int. They have to actually be the same type. Let's look at another one. Fmap of show. Well, as long as the thing in the left part is showable, then I get back a functor containing strings. So like if I say, oh, is I need to say, tell me the type, and it says, oh. Okay, I had something funny going on. Let's see. Right, that's correct. Okay. What about like, you know, this could be, you know, like maybe bool. And it's going to return a maybe string. So I could say like, you know, fmap show just true. And it's going to return just true, where true is a string. If I say fmap show nothing, it returns nothing. That is a maybe string, an instance of the maybe string type. Now, one that we haven't really talked about much before is either. So remember that I can go up here and say, like, either has two types. It's built in, so I'm not going to load this. I'm just going to say, what's a type of, that means that there's two constructors. There's left, and left takes an A and returns an either A, B, and right takes a B and returns an either A, B. So how can this be a functor? Because we only have what would we do with fmap? Well, and plus, I mean, the first thing is that either is expecting two arguments, an A and a B, before it returns something of the right type. So like I did with functions, I can plug in and I can say, okay, suppose it's an either A. Now that means that this is the part of the functor that I'm going to be operating on. Now I can say fmap of f over left x, and there I can't do anything. Part of the either is the right part, that's the container. So that's how fmap's defined on either. So that means like I can say like, fmap of, +1 left 1, and I just get back left 1. But if I do right 1, I get back 2, right 2. If I say fmap, whatever, show over right 1, I get back right with the string 1 in it. If I do fmap of show over a left, let's say of unit, I just get back left of unit. So the mapping part only works on the right part of an either. That can be useful because, either works a little bit like we're going to see later, like maybe you can kind of catch errors with it. But what you could do and with an either is instead of just saying nothing when something bad happens, you could put a string in there and say, oh, left, and then say the string. This is why an error arose. All right, now what about applicative functors? What's applicative? Well, before I do that, class applicative, let me just say a few things. Is that so? What we don't have any reasonable way to do, there are two things that are missing with functors in a way. We don't have a way of injecting, we don't have a way of taking an element of type A and putting it into a functor of type A. I don't have a way of for each individual functor, of course, I can do something like, I can say like, if I want to inject, I can say for list, for example, if I want to have a list containing 1 in it, I could do that. So I could have a function here that says, lambda x arrow list containing x is my function, and I'll apply that to 1. Okay, and that injected And I could say, X, Y, Z, Z, Y, and that gives me a list containing that one thing, and I could put, compare 1, comma, A in it, and now I have a list containing that, and so forth. So, but then if I want to do into the maybe type, I got to go just, and so now I could say 1, and now I could say X, Y, Z, Y, and I get to just X, Y, Z, Z, Y, and I could have a pair 1, comma, A, and I get to just 1, comma, A. So in general, though, see, to write this, I had to consider the constructors for the type that I'm writing it for. And so what we'd like is a type class that captures this. Now, the other thing that we don't have is, suppose that I had like a list of plus one of, let's say, functions. Okay, so what's the type of that? A list of functions mapping numbers to numbers. What's this one? Let's see. Maybe. Not maybe, just is the constructor I want. Type is maybe. It's a maybe of a function. But now I don't have any way of, if I had a functor that contained a function and I had another functor of the same kind that I wanted to apply the function to the things inside, I can't, there's really no good way to do it at this point. So what we want is like an apply operator that works for functions inside of a functor to be applied to an element of the proper input type, also inside of a functor. And so this is what applicative gives us. So we could say class and it's defined, it says, as long as f is a functor, then we can make f applicative if we add the following two operators. One of them is called pure, which is the one that takes an A and injects it into f of A, and the other one is, and probably, people are confused oftentimes on what to call this thing. I call it apply because it's just apply lifted up to the functor. Like you've got containers up here, some containing functions, and you want to apply the functions in the container to, some objects in a container. And so this is, it isn't a kind of an apply. So what is it doing? It takes an A arrow B functor of that type and returns a function that takes an f of A to an f of B. Let's go check that down here. Okay, so I'm going to add the module control dot applicative just so I have access to all these things. And so now I can say like, okay, well, let's just look at :info applicative. And it basically says, oh, okay, look, it tells me a whole bunch of stuff. You've got pure, you've got apply, and you've got another function called lift2 in there. And then you've got a couple of others in there. But it says here, the minimal thing you need to provide is pure together with apply or pure together with lift A2. So we'll talk about lift A2 in a little bit. But what is pure? So pure is the one that injects elements of the thing that are supposed to go into the functor, but it's very general. So like if I go down here, we can also look at zip lists are replicative, monads are replicative, something in this arrow type. Either E is applicative. You can only apply using the right side, the right constructor, not the left one. Lift is applicative. Maybe is applicative. IO is applicative. Functions with domain A are applicative. Pairs are applicative, where the first element is the part that's fixed and the second element can be thought of the container. So let's see. If that's true, then I should be able to say F map of, like +1 to a pair that's a string and 2, and it'll work. But if I did it the other way, I'd have problems. This is not going to be well typed because +1 doesn't work on the second element. So F map only applies to the second element of the pair. So let's go back and look at the info again for a bit. Here's the various things. Okay, so how can we make, for example, instance, maybe is applicative. How can we make maybe applicative? Well, we got to define pure, and pure is the thing that takes an X and injects it into a maybe. So the only thing that we have to do that is just. And now, if I had a just with an F in it, and I wanted to apply that to a just X, that's going to be equal to just F of X. Now I have to also take care of the cases where there's nothing. Where nothing appears. So I got to say, okay. The second argument is nothing, then I return nothing. And similarly, if the first argument is nothing, and I had some kind of, I don't even really care. That's equal to nothing. Remember that I don't know. Okay, I have no idea what this editor is doing half the time. Why won't it let me line these things up? Okay. We probably could simplify this by just saying, in any other case, nothing. Only if they're both justs that we get something back. All right. Now, what do we want to say about this star thing? So that's for maybe. So that means I can do something, and that is already defined. So I could have like, just, uh, let's see, here's an interesting thing. I could say pure plus one, and now it's not going to know which type to put it into, I don't think. What's a type of pure? Oh, this is actually confusing to me. I don't know. It's saying it's going into a functor, but they're displaying it back to me, or I mean, they're letting me do this and not complaining. I would think they don't have enough. Now, if I say pure plus one, and I want that to be a maybe int, it's a maybe int arrow int, sorry. That's okay. So I can use it this way. I can say pure plus one. And so that's the right kind of thing. And I can apply that to using the star to a just two, back three, say like times two, back four. Now I could also say pure times what's going to be the type of this. This makes sense. Pure. So inject the multiplication function into the maybe monad, and then apply that to a instance of maybe of the form just two. And the type of that is it's going to be waiting for it's a maybe of an A arrow A. So if I want to plug in the other A, I could say, just three. And I don't want to know the type anymore. I just want to do it, and I get back 6. If I want to do 2 times 3, I can inject this into the maybe monad. So that's the same thing as writing just times, because that's how we inject it into the monad, times just 2, or applied to, I'm sorry, this thing is really applied to just 3. And so that's working out kind of like what you expect. I mean, if you take times and 2, what's the type of that? It's going to be, it's a number still expecting an argument. If I give it a 3, I get the full string. So at the flat level, but now I'm working up inside the maybe monad. Let me see. What else do I want to say about maybe or pure? Oh, pure doesn't necessarily know which way to go. So if I say pure 7, and I want that to be a maybe int, now I get the just constructor. If I say pure 7, and I give the hint that I want this to be an int list, then I get the list constructor. If I say pure 7, and I want this to be an either string, I can't give it the string. I got to give it the, what's going on here? Yeah, let's see. No, it's not. Pure 7 isn't either. Maybe I need to do this. I need to tell the whole type. Okay, there it is. Right. Change this type to be anything. You know, I could change this to be list of strings, and that still works. But it just injects it into using the right constructor because that's the way either is done. Did we do either up here? Yeah, we did. No, we did it as a functor, and we didn't do. Let's do instance. Um, so pure is going to be equal to right, and if I have a right f applied to a u, a all right, applied to a right x, that's equal to right f applied to x. If I have anything else, I need to write it out though in this case because I need to get the need to be able to retrieve the left part because it just revalues. So if I say left, see, I am not sure if I need those parentheses and say right x left z. Now here we have to worry a little bit. And it's going to be the first one that failed. I'll call this Z. Call this one X, and then leave, so that reads the same. But it's going to sort of keep propagating along the earliest thing that failed. I'm going to assume I don't need these parentheses. We'll check it. Let's go check it. Let's say like right plus applied to, let me make it +1 so it completely evaluates. Applied to right 2. I don't need the parentheses. But if I say like something like that, I get back left X. I should have said left Z. If I do this, and it really doesn't matter what I have on this side. I have like a right one. Just back to left Z. If I have another left, back to left Z. See, so yeah, I didn't load this. I was just showing you the definition, and here's the one that's built in, which matches what I've given it. Oh, here's maybe an interesting thing with pure. You can say like pure and applied to pure 7 could be a list of maybe int. And that gave me that. I could say, oh, it's maybe type is telling the system what pure to look up. So what's happening with these type classes is it's running across this and it's saying, okay, 7 is a number type, and pure can take an A and inject it into what? It can inject it into lists and all the things that have been declared to be applicative. And so I inject this in, and then the $sign. What does $sign mean? I mean, $sign is useful in writing code to make it look a lot simpler. It's just same as apply, right? +1 $2 is 3. I need it. I could just write it like this. But the reason it's useful is because there may be a whole bunch of things here that I want to apply together, and I can write it like that and it works. But if I didn't have it like that, I'd have to say like, what if I do that? Okay, I've got a problem. So I need to use the $sign to kind of I could group these things together like this, or I could group these things together like this and get rid of the compose. But it's kind of nice sometimes to just simply read compositions following dot, 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 and then followed by a $sign. All right, now what about the list one? The list one is a bit weird. We can first look at it. I can say like, oh, +1. All right, let's do +1 times 2 and apply that to the list 1, 2, 3. Now I get back 3 things. I'm sorry, 6 things, 3 things twice. So I'm getting back, these 3 are the result of applying +1 to them. And then the second things are the result of applying ×2 to these elements. If I swap these around, you'll be able to see that the 2, 4, 6 move to the front and then 2, 3, 4 move to the back. So what's going on there? Like, you might have thought like zip is, like it just pairs up and says, oh, this list is longer than this one. Just throw the tail away. This could have been like 2 times 1, and then the second element could have been 2 plus 1. But instead, it applies this function to everything here. Now, some people like to think of this as like modeling, and it might be useful in some cases to model non-deterministic computation. What if I had a function like that wasn't a function, it was a relation, it returned more value? Suppose like I had all right, suppose I had like, 1F2 is in the relation and 1F 4 is in the relation. Well, one way I could make this into a function is I can grab these things and say, okay, f of 1 is equal to, and give all the answers that it could be. And so then the way to think of it is like if, this could have been the result of some previous non-deterministic function. The result of the function was either times 2 or was plus 1. So you say, okay, we'll put those together as one answer. The list itself is an answer. And so now if I have a non-deterministic set of functions and I'm applying it to maybe the result of another non-deterministic computation, what could have returned 1 or 2 or 3, well, I want all possible things that could have happened. 2 could have been times 1, and if this had been return 2 and this had just returned 1, or times 2, 2, or times, so, and then you get all the possible answers up here. So how do we do that, though, in the well, pure is easy. You just make it a singleton x. And then, so if I've got some function list, some f's, and I've got some x's, now what am I going to do? I'm going to return f of x. And, the list comprehension notation makes this very simple right down. I'll say f comes from f's. X comes from x's. And that's the definition of that. Oh. That's a V. Okay. I think if you try to do it the way that you do zip, you actually end up breaking one of the laws, the associative law. So, now you can write, you can do stuff like, what's the type of, if for lists, I could write, pure 1 plus pure 2 or 3. And I get the list 1, 3. That's because this is injecting into a list and that's injecting into a list. So I could like say pure plus 1 and pure, let's say times 3. And they don't know how to show that to me because it's a list of functions, but I can take that and then I can apply that to the list of 1 through 10. Now I should have 20 elements in there. There's 20 elements in there. What about with the maybe? We did that. I think we did the either. Pure 1 plus 1 plus, if I'm right, works. Now, one of the things that's when applicative also defines a new operator called an infix form of fmap. Since it's just fmap and infix, we just call it fmap. Oh, I got to put parentheses around it to make it a section. And so if you look at fmap has exactly the same type. They're exactly the same function. It's just that this is a nice infix name for it. All right. What about lift A2? What is lift A2? Lift A2, and it's a function, so it's lowercase. Well, it takes a 2-argument function and then applies it to 2 functors containing things of the right type and returns a functor of the other type. So what it's doing is kind of lifting up an A arrow, B arrow, C. It's a little bit like map. See, like map is taking an A arrow, B and lifting it up to a functor of A arrow, functor of B. And this was taking an A arrow, B arrow, C and lifting it up to a functor of A arrow, functor B arrow, functor C. You might, I think there's actually lift A3. Yeah, so that's a function of 3 arguments. How far do they go? 4. No. Okay, so let's look at like lift A2. And ordinary plus, and so then I can say like, just 2, just 3, and that's going to return just 5. So I've kind of lifted this up to be able to work with these arguments. We can define lift A2 F and this is really, well, okay, so let me call this G, and then I can say functor of let's say, whatever, A. I don't want the type, though. Lift A2 G X Y is equal to F map F over X star Y. But with this new notation, this dollar infix notation, we can rewrite this as I don't know, in a maybe a nicer way. We can write down here. We can say apply F to X applied to Y. Well, and in fact, I don't need these parentheses here. Okay, so quickly, let's look at what are the laws of the applicative type class, if you were going to, create some new ones, you want to make sure that these hold. One is that pure ID applied to any V is just equal to V. So if you, that's lowercase. If you inject the identity function into a functor and then apply that to a functor V, you just get back V. And you have let pure. This is a kind of associative law. If I take the function composition and I inject that into U applied to E. So now I'm applying the functor containing the function composition first to U and then to V and then to W, and that's equal to U star V applied to W. So this is a kind of associative law. The third one is that pure F applied to pure X is equal to pure F applied to X. That one would seem to make good sense. And the final one is a little bit weird. It says that U applied to pure Y is the same thing as $Y applied to U. Okay, so what do we get? This one's a little bit weird, but so what is $Y? Remember, the type of dollar. I got to put parentheses around it. It's just apply, except that it's an infix form. So I can like say like something like $10. Now I could apply that to, now remember this thing here is going to be, instead of, maybe I'm just talking about up at the bigger level. So now I'm going to need a function, so $10 is like an argument waiting for a function to come along and be applied to it. So this is waiting for a function. I could go the other way. I could say like, I mean, this is just silly because it's just the same thing as times 22 applied to 10. This one's kind of interesting. It's saying like, okay, if I apply U to a pure Y, that's kind of like Y waiting around to be applied, waiting around for U to be applied for it. And I think, like I said before, if we did the list apply, the functorial apply function, define that for lists the way we do zip, and just said, oh, if the lists are not the same length, and just throw away the stuff on the longer one, I think then that associative law fails, is what I recently read somewhere. Okay, so that's a lot of stuff about control and applicative. I really recommend that if you are a programmer, go back and look at this note, this announcement that I made. If you're a JavaScript programmer, best JavaScript functional programming guide in a few videos. And then if you click on this, I can open it in a new tab. And it's Professor Frisbee's Mostly Adequate Guide to Functional Programming. I recommend take a look at this. I think you'll find, first of all, you'll find nice explanations. If you're still struggling a little bit with curry, there's a lot of stuff in here about curry and how you do curry in JavaScript. Let's see. Well, you can look at it. I won't ruin that. Okay, thanks.